Okay, in this video we're going to look at finding the first and second derivative and the tangent line at x equals 1 to this function. F of x equals 4x squared minus 3x plus 1 divided by 5x cubed plus 7. So we have a rational function here. If you haven't worked this one already, please go ahead and do it now. Press pause. Okay, so, we see that the last thing that you would do if you were evaluating this function is to divide. So the outermost function is a just division function. So we use the division or quotient rule. So the quotient rule says you take the bottom denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. Okay, so bottom times derivative of the top minus top times derivative of the bottom over bottom square. Well, all these are just polynomials, so we know how to do these derivatives. The derivative of 4x squared minus 3x plus 1 is 8x minus 3 plus 0. And the derivative of 5x cubed plus 7 is just 15x squared. The derivative of 7, 0. Now we have the derivative, that the calculus is done. We just need to do some algebra here to clean this up. We're going to use FOIL here to distributive property to multiply these out. 5x cubed times 8x is 40x to the fourth. 5x cubed times negative 3 is negative 15x cubed. 7 times 8x is 56x, and 7 times negative 3 is negative 21. Now I'm going to put this negative with the 15x squared and distribute the whole thing. So negative 15x squared times 4x squared is negative 60x to the fourth. Negative 15 times negative 3 is positive 45. X squared times x gives you x cubed for that term. And of course, 1 times negative 15x squared is negative 15x squared. Now combine like terms, putting them in decreasing order. 40x to the fourth minus 60x to the fourth is negative 20x to the fourth. 15x cubed, negative 15x cubed, plus 45x cubed is 30x cubed. Here's an x squared term, negative 15x squared. Here's an x term, 56x. And there's the constant term, negative 21. So there we have our formula for our derivative. And normally we'd like to try to factor this numerator if possible, but there we have it. There's the formula for the derivative. You can check it like you see here in the TI-84, for example. Write the original function here. Remember to put parentheses around the numerator and the denominator. For y1, turn it off. Turn y2 on, which is numerical derivative of y1 with respect to x, evaluated at x. Let y3 be our final answer here, again remembering to put parentheses around the numerator and denominator. And the tables for y2 and y3 should match. y2, of course, is the symmetric difference quotient. y3 is the actual derivative. And to many decimal places, they will be the same. So far it looks pretty good. Alright, now this will be a little bit more challenging in the next one, but it's basically the same steps. Figure out the second derivative, in other words, the derivative of this derivative. If you haven't done that one yet, go ahead and do it now. Press pause. So the second derivative is the derivative of the first derivative, so it's the derivative of this. So again, we're going to use the quotient rule, because again, that is the outermost function. If we think of this as a composition or a chain of steps, the last step in that chain is division. So we use the quotient rule. So the quotient rule says take the bottom, which is this, 5x cubed plus 7 squared, times the derivative of the top, so that's the derivative of that fourth degree polynomial, minus the top, here it is, times the derivative of the bottom over the bottom square. Now notice this brings the power all the way up to the fourth power. But something you'll see that's interesting in the end is that in the end we're going to only end up with actually third power here. So what typically happens is when we take a derivative, the power in the bottom goes from power 1 to 2, and then it goes from 2 to 3, 3 to 4, and so forth as we take more higher and higher derivatives. Okay, so anyway, let's see, where were we? Okay, so the squared and squared multiply the powers gives you the fourth power. Now, let's do these derivatives. So this one here, polynomial, this should be pretty easy to do. 4 times negative 20 is negative 80. Power goes down 1 to 3. 3 times 30 is 90. Power goes down 1 to 2. 2 times negative 15 is negative 30. Subtract 1 for the power is 1. A derivative of a term that has an x, just an x term, is just the coefficient, and derivative of the constant is 0. And here I went ahead and distributed the minus, so I made this plus here, but that made this plus, minus, plus, minus, plus. Plus, minus, plus, minus, plus. There we go. Now the derivative here, I did the substitution in my head this time, so see if you can follow along with me. I'll say it out loud here. Let u be 5x cubed plus 7. Then this becomes the derivative of u squared. The derivative of u squared is 2 times the u, which is this, to the first power, times the derivative of the u. That's the derivative of this part right here, which is 15x squared. Okay, did everybody follow that? So I did a substitution. Let u be 5x cubed plus 7, and this becomes a power function with the chain rule. Alright, now what we're going to try to do now is do some factoring. Okay, first of all, notice that 2 will divide evenly into all of these things here. So I can factor 2 out of this. And this one already has a 2 here, so I can bring that 2 all the way out front. And notice that they both have a 5x cubed plus 7. So that's going to come out front. Now I'll put the parentheses here, and what's left? Let's see, we factored the 5x cubed plus 7 out of this, cancels that down to the first power. And we divided this by 2, that means dividing all these coefficients by 2, so they become negative 40, positive 45, negative 15, and positive 28, respectively. Now over here, let's see what's happened. We factored out this term of this factor of the 2 and the 5x cubed plus 7 with that factor. We're left with the 15x squared, and we're left with this quartic polynomial here. Alright, so now let's see what we can do. Well, the first thing I can do is, let's see, I can do a couple of things. One thing I can do is I can cancel this 5x cubed plus 7 in the front, since it is a factor of the numerator, and it's also a factor of the denominator, so I can cancel that. And so that goes down to the third power. And again, like I said earlier, that's typically what happens in these kinds of problems. Notice this 5x cubed plus 7 is here. The quotient rule requires us to square it, so the power doubles in the bottom, going up from power 1 to 2. When we do the quotient rule again, we double the power in the bottom again, so now it's up to 4. But typically what happens is when this other factor is out here, and so it actually ends up only going up by 1 in the end, because so the power goes from 2 to 3 here because of the canceling that occurred. Alright, so now what's left in here? Well, let's see. Here we do distributive property to multiply this out. 5x cubed times negative 40x cubed is 200, negative 200 x to the 6th. 5x cubed times 45x squared is 225 x to the 5th. 5x cubed times negative 15x is negative 75x to the 4th. For the x cubed term, I got to be a little bit more careful. Let's see, 5x cubed times 28x cubed plus 7 times negative 40x cubed combines to give me negative 140x cubed. And then for the x squared term, it's the 7 times the 45x squared. That should be 315x squared. The 7 times the negative 15x is the negative 105x, and the 7 times 28 is 196. So when I multiply these two polynomials right here, I get this 6-degree polynomial starting right here, going all the way down to the 196. Over here, I just distribute the 15x squared. So 15x squared times 20x to the 4th is 300x to the 6th. And then I have 15x squared times negative 30x cubed is negative 450x to the 5th. 15x squared times 15x squared is 225x to the 4th. 15x squared times negative 56x is negative 840x cubed. And 15x squared times 21 is 315x squared. Now combine like terms in the top. 300x to the 6th minus 200x to the 6th is 100x to the 6th. 225x to the 5th minus 450x to the 5th is minus 225x to the 5th. Negative 75x to the 4th plus 225x to the 4th is 150x to the 4th. Negative 140x cubed minus 840x cubed is negative 980x cubed. That's good. 315x squared plus another 315x squared is 630x squared. And then we've still got these two terms right here that don't combine with anything, so they come straight down. Now, we would like to factor out this in the top if we could. Let's see if there's a constant that we could factor out. Well, the only thing that divides into 100 evenly is prime numbers are 2 and 5. This is 2 squared times 5 squared. That one has some 5s but no 2s. This one has some 2s, but that has 2s and 5s. The last one has 2 but no 5. So we can see that there's no constant number that could factor out. This may or may not factor out into some other factors, but certainly pretty sure this one down here is not one of them, so it's not going to reduce anymore in terms of any canceling. So there we have it. We can check that. Since I already had f prime, this formula right here, placed in y3, I went back to y2 and changed it to be the numerical derivative of y3 with respect to x, evaluated x, turned off y3, let y4 be my final answer, which is what I have here. It went over to the next screen so you can see it better here. Right here. And then did my table for y2 and y4, and sure enough they match. So that was a good check there. So I know that I got that correct. Okay, now we also wanted to find the tangent line when x equals 1. So we go back to the original function right here and plug in 1. So that's 4 times 1 squared minus 3 times 1 plus 1 over 5 times 1 cubed plus 7. So let's work this out. 1 cubed is 1 times 5 is 5 plus 7 is 12. This is 1, 1. So this is 4 minus 3 is 1 plus 1 is 2. 2 twelfths reduces to 1/6. So the point 1, 1/6 is a point on the graph, and it also needs to be our point on our tangent line because we want it to be tangent at that point. Now, to find the slope of the tangent line, you go to the derivative formula, which was this one right here, negative 20x to the fourth, etc. Take that formula, replace all the x's by 1, and see what that reduces to. Let's do the bottom first. 1 cubed is 1, times 5 is 5, plus 7 is 12, squared is 144. In the top we have negative 20 plus 30 is negative 10, positive 10 plus negative 15 is negative 5, plus negative 21 is negative 26, plus 56 is 30. And looks like I can cancel out a 6 here. 30 divided by 6 is 5. 144 divided by 6 is 24. So that reduces to 5/24. So our tangent line is t of x equals the slope, which is f prime of 1. And that should say f prime not at x, but at 1. Okay, and which is 5/24. Then you have x minus 1 plus the y value 1/6. So when I graph this, the point 1, 1/6 should be a point on the tangent line and the original curve. You can see it right there where my cursor is. See that? And notice that the graph touches the tangent line at that point. And nearby, if we were to zoom in on this part right here, we see that the graph of the tangent line and the graph of the original function are pretty close. The blue one's the original function, which is in 2 pieces. Now let's analyze these graphs just a little bit. So let's see, that was our check. Okay, so we go back up here, look at the original function. Notice that if x is the cube root of negative 7/5, or negative, the opposite of the cube root of 7/5, that's going to be where this one is undefined, which is going to be a vertical asymptote. And of course, it's undefined. The first root is undefined. The second root is all undefined at the same point. So that's this guy over here, somewhere to the left, just a little to the left of negative 1, it looks like. So you see vertical asymptotes on all 3 functions right there. Let's do end behavior next. If you take the limit as x goes to infinity, since the bigger power is in the denominator, this thing is going to approach, the original function is going to approach the x-axis, y equals 0, on both the right and left ends. So we should see an asymptote there on both ends, which we do. Notice that the end behavior of the derivative and the second derivative are also approaching the same thing, I believe here. Yes. This is all together is an x to the 6th power here in the denominator, which is going to dominate over this x to the 4th. So this thing is going to go to, the bottom's going to go to infinity faster than the numerator, enough so that we know that this limit is 0. And similarly down here, this is a 9th degree polynomial in the denominator, which is higher degree than the numerator. So all three of these functions, the original, the derivative, and the second derivative, all approach the x-axis as we go to infinity or minus infinity. So they all have a horizontal asymptote. Okay, notice that the original function, 4x squared minus 3x plus 1, let's see, that factors actually is 4x minus 1. Let's see if I write this down. I think, let's take a look at this. I think I can use anti-FOIL factoring here on this. Let me see, let me check this to be sure. Well, if I do, it's going to be a 4x and an x to get the f to work. And both the signs need to be, no, it's not going to work. If this being a positive at the end means both of these are the same sign as the middle, and the only thing to check would be this one, and that actually gives you the wrong middle term. That's negative 5x, not negative 4x. Had this been a negative at the end, I think we could have made that middle term work out, but it wasn't. Alright, so that doesn't factor nicely. So what does that mean? That means if I'm going to find any, if I want to factor it, I have to use the quadratic formula, or equivalently completing the square, and see if that if it ever actually hits 0. Let's take a look at the graph. It's a little hard to tell from the graph, but it looks like it never actually hits 0. It looks like here actually the graph is above the x-axis and then never actually hits 0. So probably when you do this with the quadratic formula, you end up getting the only roots of this numerator are non-real complex numbers. So looks like we have a minimum there where the derivative is 0. Where does that happen? Well, okay, that's harder to see. This is a 4th degree polynomial. It could have up to 4 places where it hits the x-axis, but it looks like well, it looks like it hits it once in here for a minimum. Another place over here it hits it again for a maximum there. And then from there on out, it's hard to tell from looking at this. It looks like it doesn't actually hit it again. So it looks like probably this 4th degree polynomial here has 2 real roots and 2 non-real roots. And so the real ones happen somewhere about here and about here. That's about 0.4-ish and 1.7 or 8, something like that. Roughly speaking, just looking at the graph. The red graph here is the graph of the derivative. When the derivative does touch the x-axis, the original function has a maximum or a minimum. In fact, this has a minimum right here at this first one and a maximum right here at this one over here. So looking at this part right in here, the functions from the asymptote going to the right, it's decreasing. The original function is decreasing concave up. And notice that it's concave up because the second derivative is positive here, or the second derivative is positive because it's concave up. Either way you want to look at that. And then it reaches a minimum here, and it starts to increase here. The original function increases where the derivative becomes positive, but the second derivative is still positive, so the original function is concave up. Now, somewhere about here, along the lines of about 0.8 or so, the second derivative is 0. So this 6th degree polynomial here is actually equal to 0 at some point there. Looks like that's the only, maybe the only place. Hard to say. No, looks like there's another place over here. Looks like there's probably 2 places where this touches the x-axis, and then 4 non-real roots. So one of them is right about here, And so this was going concave up, decreasing, hits a minimum, still concave up. When the second derivative is 0, then it switches to concave down, still increasing. When the first derivative hits 0 over here, then we've reached a maximum on the original function. Then from there on, the first derivative is negative. It's coming down and then coming back up closer to the x-axis, but staying below it. And so this is decreasing from there on out. However, it's decreasing concave down, and then somewhere up in here it switches to concave up on the last piece to the far right. So there is a place somewhere in here. It's hard to tell where it is exactly on this thing, but wherever that green second derivative graph crosses the x-axis, then the original function has an inflection point. So we might bear some further investigation. A close-up of this part of the graph might show some of those interesting features a little bit better. Okay, let's see what else. Over here on the far left, they all approach the x-axis. Over here on the left, the original function is decreasing concave down. That should say, since the original function is decreasing, the derivative should be negative, and we see that's true. And the second derivative should also be negative because this is concave down on the original function, and that's also true. And so I believe that gives us a pretty good analysis of that particular function. Now, the next video, we're going to look at the function f of x equals natural logarithm of 3x to the fourth minus 2. And we're going to ask that you go ahead and find, once again, the first derivative, the second derivative, and the tangent line at x equals 1. Maybe graph all those together, and then examine what happens with the graph characteristics, and check them in your calculator like we did with this last example, last several examples. So if you haven't done that one already, be sure you do that before watching the next video.